All right, this is the second review video for Chapter 2A, Electric Forces and Fields. This one's just dealing with Coulomb's law. I'm not going to get into a lot of the nitty-gritty details or background history or stuff that we talked about in class in terms of this. I'm just going to try and refresh your memory about this equation and how we use it. Okay, so the other, another really important part about this that I'm not going to get into great detail is how similar it is to the gravitational force formula. So keep that in mind as well too, and make sure to review your notes and your work booklet as always in terms of refreshing your memory and practicing this concept. Okay, so the equation we usually call it the electrostatic force, so that's why there's a little subscript E there. K, Q1, Q2 over R squared. This formula explains the electrostatic force between two charged objects a certain distance apart from each other. Okay, each of these objects has a charge on it as well too, and so the electrostatic force is directly proportional to the product of those two charges. Okay, so the larger that the charges are, the greater the electrostatic force is. As you can see in this formula, that the distance between them is an inverse square. So the further apart that these objects are, then the less the electrostatic force is going to be, okay? And inverse square proportionately, right, as well. Okay, so this is our electrostatic force, and this is my distance apart. It drops off very, very quickly, okay? The other thing that you notice in this equation is the electrostatic constant, K. And so this value is 8.99 times 10 to the 9, which is significantly larger than its counterpart in the gravitational force formula, which was a negative value. So this obviously helps to calculate the electrostatic force along with the relationship of the charge product and the distance squared between them. Okay. So other than that, we practiced in our work booklet, a bunch of scenarios where we rearrange this formula for the electrostatic force, solving for Q, solving for R, just, practice manipulating the formula and that sort of thing. So this formula describes two objects. Now, in our practice and when we deal with this on a regular basis in physics, it's not always that we're going to have just two objects. So you can have three objects and they don't always have to be linear as well too, right? So I'm just going to go through that really quickly, what happens when there's more than two objects, and also when it's not linear. Okay. So if I had three objects here, objects A, B, and C, and let's say that the question was asking us to find the electrostatic force on object C due to the other ones. In order to solve this problem, you basically are breaking it into two separate problems. You're going to take a look at the electrostatic force due to A. So we're going to take, we're going to take this B one, right? And pretend that that one's not there anymore, okay? So we can take the B out there and we can find the electrostatic force between A and C using this formula right here, okay? So we do K, QA, QC over R squared, find out what that value is. Then we do the same thing with B and forget that A is there, right? Find out what the electrostatic force is between B and C. Okay. Once we've found out those forces individually, then we can put them together into a net force equation. Okay. So our F net for this would be equal to F A and C plus F B and C. Okay. Pretty simple. Only catch to that is we have to determine if those forces are positive and negative. The electrostatic force can be an attractive force or a repulsive force, okay? And remember as well too that we don't get that from the actual formula. When we substitute our Q1 and our Q2 into this formula, we don't put them as positive or negative because that doesn't help us to determine if it's a positive or negative force, okay? What we have to do is we have to look at the given question and apply from the question if it's a positive or negative. So let's just say this was positive, negative, positive, just for the sake of this example. Okay. If that was the case, if we're looking at A and C here first, right, we're always looking from the perspective of C because this is the F net on C. Okay. If there was just A here, C would be repelled from A because they're both positively charged. So that would cause C to move to the right. So the right is a positive. So I'll put that as a positive force. Okay. Now between B and C, if there was just B and C here, C would be attracted towards B because B is negative and C is a positive, right? And so that would be a force to the left. So that would be a negative force. So I'm going to switch this positive sign in between here to a negative sign. Okay. So when we added them up together, then we'd have a positive force of A on C minus the force of B on C. Okay, and that would give me what my net force would be acting on C. Now that's for a linear example, right? Obviously, we can have a non-linear example. So some of the examples that we had in class, you know, these ones, something that looks like this: A, B, and C. And these two-dimensional questions, they work basically the same way in that we're going to find the net force between two objects first for all the different scenarios, and then we're going to put it together in a net force equation. Okay, so let's again pretend in this one that it was C again that we're trying to find the F net on. So I'll just write down here, F net on C. In order for me to find the F net on C, I'm going to have to find the electrostatic force between A and C and between B and C. Okay, so electrostatic force between A and C and electrostatic force between B and C. Okay, we do that separately. Okay, so we would do K QA QB over R squared. Okay, and find out what that value is. We do the same thing for here, K QB QC over R squared, and find out what that value is. Okay, now unlike the one that we just did above, we can't just add these together as positive or negative because they're not linear, right? So at this point, we'd have to do a two-dimensional analysis where we break each of these down, the first one, A and C and B and C, into the X component and the Y component, okay? For A and C here, you can see that it has an X component and a Y component, so we'd have to do Pythagorean theorem, or not Pythagorean theorem, pardon me, we'd have to use trigonometry to determine what your X and your Y values were, okay? And in order to do that, obviously we need to know what this angle is, so we'd have to do a little bit more math before we could figure that out. Okay, once we know what this angle is and we know what the force is between A and C, then we can find our cos, which would be our X, and our sine, which would be our Y, based on the angle that I drew on here. Okay. For B on C is a little bit easier because it's directly in the vertical. There would be no X component for B on C, okay? But there would be a Y component. So whatever we found here, this would be our Y component for the force. Then, as we have done since Physics 20, we do a two-dimensional analysis. We find our X total, our Y total, add them up, draw a new right triangle, right? And when we draw a new right triangle, then we get then we can do Pythagorean theorem and inverse tan to find out what that angle is. And you have some examples in your work booklet where we do two-dimensional analysis for Coulomb's law. So I highly recommend that you take a look at those examples. They're a little bit longer, right? Because you're doing multiple equations in one question, right? You're doing the Coulomb's law a couple times, and then you're doing a two-dimensional analysis. So they're longer. And whenever it's longer, there's more chance to make little mistakes as well too. So just be aware of that and check your work regularly.